Ok, da questo momento stiamo registrando, quindi direi che possiamo iniziare. Mi confermate di nuovo che vedete la slide e mi sentite?
Sì, assolutamente.
Benissimo.
Professore, posso fare una domanda subito?
Certo, vai.
Per la registrazione, dopo la troviamo nel canale YouTube, come funziona? Perché non ho ancora capito.
Allora, se è come l'anno scorso, c'è un link nel sito del Dipartimento di Fisica e Scienze della Terra, in cui tu vai a cliccare lì, lo trovi in basso a destra nel sito nella pagina web del Dipartimento, e lì accedi a tutte quante le lezioni registrate online. Basta seguire, è abbastanza facile. Se hai problemi dite, poi ne parliamo dopo, oppure chiedi a Gambetti, agli informatici. Comunque, insomma, vanno automaticamente lì. Non immediatamente, passa qualche ora perché Gambetti deve prima scaricare dal suo drive e poi caricarle lì.
Ok. Comunque se si perde qualcosa può sempre essere recuperata, per esempio se non si può seguire una lezione si riesce a recuperarla, insomma.
Sì, idealmente le registreremo tutte, saranno tutte disponibili online.
Ok, grazie mille, grazie.
Ok, ci sono altre domande del genere? Adesso vi spiego un pochettino come funziona il corso, quindi magari le domande vengono dopo. Ok? Okay, so I will now switch to English. So let me start with a brief introduction to this course. Okay, so you know I'm Dr. Papalardo from the Department of Physics and Earth Science. And as you know, the course is 6 credits. This corresponds to 54 hours of front lesson. And the lessons are scheduled, as you see and as you know, on Wednesday, 9 to 11, and Thursday, 11 to 13. Although there might be changes during the semester, if needed, okay? And this will be, you'll be informed, of course, in advance in case of changes. Now, the course consists of theoretical lessons and also exercise. The lessons are provided partially on the blackboard, actually a whiteboard, and partially through the projection of slides. And the slides will be uploaded online the day before the corresponding lesson. So today already you have online available the slide that I will be showing now. So you just need to go to the web page of the course, you go to lecture notes, and then you will find the lecture. Okay. So today's lecture is already uploaded, and tomorrow's lecture will be uploaded today later in the afternoon. Okay. So the idea is that if you want to, you might want to print the slides and take notes on the slides, or just have them online, as you prefer. Now, a few words about the content of the course. So the course is divided in 10 modules, or 10 chapters. Today we'll start with module 1, which is essentially an introductory module. This will take 4 hours, so this means 2 lessons, today and tomorrow. So we will start with a very quick and simple introduction to the standard model of particle physics and fundamental interactions. These are all things that I expect you know already. It's just a reminder. And then we will start a summary of relativistic kinematics. So we'll start with some very, very basic relativity, special relativity today, and tomorrow we'll go in some more detail about reaction, center of mass, laboratory frame, and so on. The second part we'll start next week is about basic concept. So there are very important things that we will be using all over the course. So the Fermi-Golden rule, how to calculate cross-section, decay rates. Then will be a chapter about the Dirac equation, which is a fundamental, as you know, quantum relativistic equation for fermions. We will introduce the Lagrangian formalism that you already know from previous courses, from quantum mechanics, for instance, and the concept of symmetries and conservation laws. Then will be a very important chapter on quantum electrodynamics, which is the first gauge theory that we will study this year. Well, I will not go into detail here, but we will, of course, discuss and derive the Lagrangian of QCD, the Feynman approach with the Feynman diagrams, and also we will be able to calculate the cross-section of some relevant QED processes. Then we will switch to a short chapter about the discrete symmetries. So we'll discuss here about parity, charge conjugation, time reversal, and CPT theorem. And then we will start a quite long chapter about hadrons. So here we will discuss in quite in depth the properties of hadrons, the classification of hadrons, so mesons, baryons, the multiplets, the theoretical framework to understand these multiplets, so the SU3 flavor symmetry and the quark model. And then we will also move on to the heavy quarks and the heavy hadrons and resonances. The next chapter is quantum chromodynamics. This is the second gauge theory that we will encounter in our course. It is the gauge theory of the strong interaction, as you know. This will take 2 lessons, so essentially 4 hours. So we will introduce the Lagrangian of QCD. We will study the quark-gluon interactions. We introduce the concept of color factors. And then we will study some relevant phenomenology of QCD, that is confinement, asymptotic freedom, hadronization, and how these things have been studied experimentally. And then at the end, we will also mention about the quark-gluon plasma. The following chapter, number 6, is about the structure of nucleons. So it's a very important chapter, again, 6 hours, so this corresponds to 3 lessons. So we will study in some detail how the proton is made of. And we will start from low energy electron elastic scattering processes, and then we will go more and more in detail, increasing the energy. So we will switch from elastic to inelastic, and then from inelastic to deeply inelastic. We will introduce the Parton model and the modern view on the internal dynamical description of the proton. Okay. Next in the list is another big chapter, is about weak interactions. Okay, so we will start from the very basic, so the beta decay and the Fermi theory, and then we will discuss the experimental discovery of parity violation in 1957, and this will bring us to the charged currents of weak interaction and the V-A theory. Then we will discuss the weak interaction for quarks, so the Cabibbo mixing and the CKM matrix, and also the Jim matrix, which is also very important. We will discuss from the experimental point of view how the weak bosons, so the W and the Z, have been discovered. Then we will have a chapter about CP violation and oscillation of the neutral mesons. And finally, a chapter on the phenomenology of neutrino oscillation and the PMNS matrix. Then we have, let's say, the summary of all we will have learned at that point, that is essentially the standard model of particle physics. So this is about electroweak unification and the Higgs mechanism altogether. So we will study the couplings of the Z and the W, and most importantly, we will derive step by step the Higgs mechanism, which is, as you know, a crucial mechanism that allows to provide mass to the massive particles. And this will, so we will conclude this chapter with a global view of what we know today about particles, fundamental interactions, and of course, the standard model, which is the quantum field theory of all of that. And the last hour, so this is the very last lesson, we will discuss about physics beyond standard model. So we'll touch very briefly dark matter, supersymmetry, grand unified theories, strings, etc. Okay. Now, what about exams? So the final examination is oral, and it covers, in principle, the entire content of the course. But the student can start the exam with an argument at his choice that can be chosen among modules 3 to 9. Here, I just ask you to avoid modules 1, 2, and 10 because they are either introductory or, let's say, not the mainstream. And so then at the exam, you go in the blackboard. We suppose we can do the exam in presence. So you go in the blackboard, and you essentially make a sort of short lesson on the subject that you have chosen. And this should take at least 10-15 minutes. Okay, so you choose whatever you want, and then we discuss this argument. And then this will be followed, of course, by 2-3 questions on the rest of the program. So you have to be prepared on everything, of course. About the exam, English is optional. If you want to do the exam in English, that's absolutely fine. If you want to do it in Italian, it's also fine without a penalty. It's just your choice. About the textbooks, so the majority of the course is based on the textbook that you see here, Modern Particle Physics from Mark Thompson. It is, let's say, an intermediate level textbook. It is quite formal, but not too much. So it is not an elementary introduction. I think it's the good level for this course. But I also took some other material, sparse material from other textbooks, and you find 3 examples here. Introduction to Particle and Astroparticle Physics. The second one is Particle and Fundamental Interaction by Giacomelli Spure, that you might already have from the courses in the from the bachelor course. And Quarks and Leptons, the last one, is quite very advanced. Okay, it's a quite advanced textbook. Is also not, is quite old, is from the 90s, I think. And I will pick up from this book only few selected subjects. So, any questions? Feel free to ask anything about the program, about the exams, about whatever you want. No questions? Can you still hear me from house?
Yes.
From outside?
We can hear you.
Okay.
But I think there are no questions. Thank you.
Okay. Apparently there are no questions. It was extremely clear. Okay. Okay. If no question, then I think we can start our course. And as promised, I will start the first module with a brief introduction on the standard model of particle physics and also on the Large Hadron Collider and the Large Hadron Collider experiments. I assume that you all know most of what I will show now, but of course the important thing is that what I will show now in the next 15-20 minutes we will study in much more detail all over the semester. Okay, so it's just an appetizer. So what is particle physics? So particle physics aims to study the laws of nature at the deepest and most fundamental level. And it is concerned with the most fundamental constituent of the universe, which we call elementary particles, and also the fundamental interaction between them. So what are elementary particles? Elementary particles are essentially the fundamental bricks of matter, and they are considered nowadays as essentially point-like object. That means without any internal structure. So the most fundamental object we can think of today. Now, the concept of elementary particle has evolved a lot in time. You know, by the end of the 19th century, atoms were supposed to be elementary particles. Then with the discovery of the electron by Thomson in the late 90s, in the late 19th century, and by the atomic nucleus by Rutherford, it was understood that actually the atom is not an elementary object, it is a composite object. It is made by a small, very small and positively charged nucleus surrounded by a cloud of electrons. And the nucleus itself is not an elementary object. It is made by protons and neutrons, as you know. And until the 50s of the last century, so 1950 or something, it was protons and neutrons were supposed to be elementary objects. But then, as we will study next in the course, it was understood in the early 60s that this would not be possible for many reasons. And indeed, we know today that protons and neutrons are also composite objects. They are made essentially by quarks. And at the current knowledge, so today's knowledge, we think quarks are now the very fundamental level. Okay. But you know, physics evolves in time, so maybe in 15 years from now, we will also learn that quarks are also composite. We don't know. So today we consider elementary particles, both the quarks and the leptons. We will study all these in detail, of course, but leptons is a family of elementary particles that include the electrons, that you know very well, and its heavier partners, which are the muon and the tau lepton. And the dimension of all these elementary objects, so quarks and leptons, today is estimated to be smaller than 10 to the minus 18 meters. So 10 to the minus 3 Fermi, if you like. Okay. Now, a few words about leptons and quarks. So leptons are spin 1/2 objects, so they are fermions, and they come in 3 different families. And each family has a charged lepton and a neutral counterpart, which is called the neutrino, as you know. So the first family is the electron and the electron neutrino. The second is the muon and the muon neutrino. And the last one is the tau lepton and the tau neutrino. The masses are very different, as you can see from the second column. So the electron is a very light object, as you know, it is only half MeV in mass, but the muon is order of 200 times heavier than the electron, so 105, 106 MeV, and the tau is even much more heavier. It's essentially 1.8 GeV, so it's essentially twice the mass of the proton. The neutrinos have very light, very small mass. We don't know yet today the exact mass of neutrinos. This is still under debate, and also there are many experiments around the world to try to measure the mass of the neutrinos. The only thing we know is that it is extremely small, but for sure non-zero. And the fact it is non-zero, it is of course the reason why we observe the phenomenon of neutrino oscillation. So the oscillation between different flavors, from electron to muon, from muon to tau, etc. The neutrinos are neutrally charged, and the other have a charge of -1. Also, the quarks show the same structure, so they also come in 3 families. The lighter family is made by the up and the down quark, was massive of the order of few MeV, so 2 MeV for the up and let's say 5 or something for the down. Then we have a second family with heavier quarks. We have the strange, order of 100 MeV, and the charm, which is 1.3 gigaelectron volt. Okay, this means that the charm itself is heavier than the proton. And then we go to the last family, which is the very heavy quarks. The bottom is 4.2 GeV, that is essentially 4 or 5 times the mass of the proton. And the top has an incredibly high mass, order of 170 GeV, that is something like 200 times the mass of the proton. And it is, as today, the heaviest particle ever discovered. And as you know, and as you can see also from the last column, they come with a fractional electric charge. So the electric charge of quarks is a fraction of that of the electron, either plus 2/3 or minus 1/3. Now, the interesting thing is that ordinary matter, so the universe that we live on essentially, and that we can observe, appears to be formed only by the first families, by the first generation. Our universe is made by atoms. Atoms are made by electrons and protons and neutrons, and protons and neutrons are made by up and down quarks. So all we need to construct our universe today is electrons, up quark, down quark, and then neutrinos and photons, essentially. The other families are just replicas of the first family, and they only differ essentially in the mass. They are just heavier replicas of the first family. They have exactly the same quantum number, they undergo exactly the same interactions, everything is the same except for the mass. And we don't know today why nature has provided us with these heavier families. I mean, we don't know, I mean, in the sense that the standard model itself does not provide any explanation for this, okay? Also consider that each fundamental fermion, so both quarks and leptons, has its own antiparticle. We will study, of course, antiparticle in the framework of the Dirac theory in the next weeks. And so we have quarks, leptons, but also anti-quarks and anti-leptons. And they share exactly the same properties, but they come with opposite electric charge, or more in general, with opposite internal quantum numbers. So not only electric charge, but also leptonic number, etc., leptonic numbers. And this will be studied, of course, in detail. What about the standard model? The standard model is the current theory of elementary particle interaction. It is a quantum field theory, and the meaning of quantum field theory we will learn in the next weeks. So it's a quantum field theory which provides a unified picture of all the known elementary particles and also of their fundamental interactions. In this framework, the interactions themselves are described in terms of exchange of particles, so other particles, which are called the gauge bosons. So they are bosons, so they come with the integer spin. The standard model, as of today, provides a successful description of basically all the experimental results that we have in hand, although it leaves open some fundamental questions. Okay, and this is the reason why there is a huge search in the world, in all laboratories, for new physics beyond the standard model. Okay, for the moment we have. I mean, we know that there must be some new physics beyond, but we don't have a clear proof from the experiments at the moment. Now, about the interactions. So, as you know, in nature, there are 4 fundamental interactions: gravity, electromagnetism, the strong force, and the weak force. And in our macroscopic world, we have, of course, a direct experience only on the first 2, so on gravity and the electromagnetic forces, because the other 2 forces, the weak and the strong force, are confined in the subatomic world. So they work only at very, very small scales, as we'll be studying. So a few words now about all of them. Gravity, it only plays a role at large scales: so planets, stars, galaxies, galaxy clusters, etc. And it is by far the weakest among the fundamental interaction, and is completely negligible at the subatomic scale. Okay, so we'll completely forget about gravity when we discuss about elementary particles. At the fundamental level, it is mediated by a gauge boson called graviton, which is supposed to exist, but it has not been discovered yet. And most importantly, there exists not today a self-consistent quantum theory of gravity. Therefore, the gravity is not included in the standard model. Okay, so we will just forget about gravity. We don't have a quantum theory of gravity, and also gravity is completely negligible at the subatomic level. What about now electromagnetic interaction? So as you know, it arises from the unification of electric and magnetic phenomena, and is completely described by the Maxwell equation and the Lorentz force. Now, there is an important difference with gravity, because it is responsible for many phenomena occurring at the atomic and subatomic scale. Okay, so gravity is completely negligible, but electromagnetism is not, and provides a very fundamental phenomena at the subatomic level. The gauge boson of the electromagnetic interaction, as you know, is the photon. And in general, electromagnetism or electromagnetic interaction plays a crucial role in the standard model, as we will study. Now, the strong force. So this is something that we don't have a direct experience in our world. First of all, it keeps the atomic nucleus bound against the Coulomb repulsion among protons. What does it mean? It means that, you know, protons are all positively charged, and when you try to put together objects which have the same electric charge, they try to repel themselves. So if electromagnetism were to be the only interaction available at the atomic scale, then there would be no way to have a bound nucleus. No way. So what we need is a stronger force, stronger than electromagnetism, with, say, an opposite direction, which allows to keep the nucleus bound despite the Coulomb repulsion. And indeed, at the nuclear scale, the strong force is something like 2 orders of magnitude stronger than the electromagnetic force. And this is why we do have stable and bound nuclei. It has an extremely small range of the order 10 to the minus 15 meter, which is, as you probably know, the size of the proton. And at elementary level, the strong force acts among quarks, because quarks are the only elementary particle that carry the so-called color charge. The color charge is essentially the strong counterpart of the electric charge. Electric charge comes with 2 signs, either plus or minus, and the color charge comes with 3 signs that we like to call red, green, and blue. We'll study this in detail during the QCD chapter, of course. Now, due to the nature of the strong force, quarks are never observed as a free particle. So there is no way, and there have been many attempts in the past, try to reveal quarks, isolated quarks. No way. And the reason for that is now clearly understood. It is a consequence of the features of the quantum chromodynamics. And this will be studied also in detail. So the only way to observe, to find quarks is to find them inside the bound states that we call hadrons. And hadrons are, of course, detected, can be, of course, detected as free objects. And there are 3 main categories of hadrons. The baryons, which come with 3 quarks, like the proton, the neutron, etc. The antibaryons, which are the antiparticles, so they come with 3 antiquarks, like the antiproton, the antineutron, etc. And then we have another category, which are the mesons, which are bound state of a quark-antiquark pair. Okay. Now, this is, of course, an extremely simplified description of hadrons. The structure of hadrons is much, much more complicated, as we will study in the chapter of hadrons and also of the structure of the proton. So the three quarks that you see here in the barren are only the so-called valence quarks, those that provide the quantum numbers of the hadron. But inside the hadron, there is an infinity of quarks, antiquarks pair, and gluons, which are the carrier of the strong interaction, and that create the so-called C, the C of the hadrons. This will be studied, of course, next. A few words about the weak interaction now. So the weak interaction is, as the name also suggests, it is weaker than the strong and the electromagnetic interaction, although it is still much stronger than gravity. Okay? And it has an extremely short range of the order of 10 to the minus 18 meters. And the reason for that, as we study, is due to the very, very large mass of its carriers, the W and the Z bosons. It is the only interaction felt by neutrinos, and this will be clear later on. And a very important feature of the weak interaction is that allows transformations among different quark flavors. The golden example is the beta decay. So you know that a neutron spontaneously decays into a proton, which is slightly lighter, with the emission of an electron and a neutrino. Okay. Now, what happens at the fundamental level is that essentially one of the d quarks of the neutron transforms into an up quark of the proton. So we have a transmutation between different quark flavors. Okay, and this can only occur through the weak interaction. In fact, as you see here, a W meson is emitted, which is one of the gauge bosons of the weak interaction. Okay, which further decays into an electron and an antineutrino. But weak interactions are also extremely useful for us because they play a part in the thermonuclear fusion reactions that occur in stars. Let me give you just as an example the proton-proton chain that we have in the sun that provides the energy at the core of our sun. Essentially, 4 protons at the end of the chain transform into one helium-4 nucleus with emission of 2 protons and several neutrinos and photons. But the first step of this chain, that is the one where 2 protons merge to a deuterium nucleus, this can only occur through the weak interaction. So the weak interaction is weak, is a very small range, but without weak interaction, the sun would not burn. We would not be here to discuss this. Furthermore, weak interaction violates some fundamental symmetries of other forces. For instance, processes seen at the mirror behave slightly different, okay? And this is what we call the parity violation, as we will study. And also particle and antiparticle may behave differently in some processes regulated by the weak interactions. And this is due to the so-called CP violation that we will also study in detail. Now, in modern particle physics, the last 3 fundamental forces, so electromagnetism, strong and weak force, are described by quantum field theory. And the interaction, as I was mentioning before, is mediated by the exchange of virtual particles that we call gauge bosons. And they all come with spin 1. They are vector particles, vector bosons. So for the electromagnetism, we have the photon, as you know. For the weak interaction, the 3 mediators are the W+, W-, and Z boson, which give rise to 2 different currents in weak interaction, the charged currents mediated by the Ws and the neutral currents mediated by the Z0. And for the strong interaction, we have the gluons, which come in 8 different combinations of color and anticolor, as we study. Now, a particle can couple to a certain force-carrying boson only if it carries the charge of that interaction. What does it mean? So all 12 fundamental fermions, so the quarks and the leptons, they carry the so-called weak charge that we call the weak isospin, and this will be studied at the end of our course. And therefore, they can interact through the weak force, all of them. Now, with the exception of the neutrinos, which are electrically neutral, all the other elementary particles, so the charged leptons and all the quarks, have a non-zero electric charge, and so they can interact also through the electromagnetic interaction. And only quark carry the strong charge that we already mentioned, we call color, and therefore only quarks can interact also through the strong interaction. Okay. So we can summarize this in this table. So the quarks can interact in either way, strong, electromagnetic, weak, and also through gravity, because they have some mass, of course. The charged leptons only through electromagnetic, weak, and gravity, and the neutrinos only through the weak interaction, again, and the gravity. Okay. Now, let's now move on to the standard model, so the theory that summarizes all the properties of the known particles. So this theory was proposed with different contribution by Gleizhov, Salam, and Weinberg in 1967, and these three guys got the Nobel Prize for this in 1979. So the main feature of the standard model is that the electromagnetic and the weak interactions are unified into one single, more fundamental interaction that we call the electroweak interaction. The standard model describes very well the properties of the observed particles. It has been very accurately tested experimentally, and the experimental test of standard model still continues in the world particle physics laboratories. So essentially, standard model parameters have been measured with incredible precision, still rising, and all standard model predictions are also experimentally verified. However, there is a problem, and the problem is that the theory from Gleizhov, Salam, and Weinberg only provide massless particles. So all the particles of the standard model come without a mass. And this is a problem because we know that many of them do have a mass. Some of them very high mass, like the weak bosons, the Ws and the Z. So what we need is to introduce a mechanism that provides the mass to the massive particle, quark, leptons, and also the Ws and Z, while at the same time keeping the photon and gluons massless. This mechanism was provided in 1964 by different people, okay? Peter Higgs, Englert, Brute, and also some other guys. And this mechanism has the power of generating the mass of the massive particle through something like that we call the spontaneous breaking of the electroweak symmetry. And this we will study, of course, at the end of our course. So the Higgs mechanism is, in a sense, the cherry on the cake, because this completes completely the picture of the standard model. So we now have a coherent theory of particle and interaction, and all the particles get the known masses through the interaction with this Higgs field. So the mechanism requires the existence of a new scalar boson. Scalar means spin equals 0. It is called the Higgs boson, as you know. It generates a field in the whole space, in the whole universe, and we call this the Higgs field. And particles acquire their mass by interacting more or less intensively with the Higgs field. So the more intense is the interaction with the particle with the Higgs field, the higher is the mass that the particle acquires. So in other words, the top quark, which is the heaviest, is the one that interacts most strongly with the Higgs field. The electron is a very light particle, it has only a very weak interaction, etc. The only particle of the standard model that do not mix with the Higgs field are neutrinos. The mass of neutrinos, which is very small, cannot be understood in the framework of the Higgs mechanism. There have been proposed several other mechanisms. We will not go into detail on these during the course. So the Higgs mechanism solved the problem of the masses, but of course there is a price to pay, and the price to pay is that we have to find experimentally this Higgs boson. If we don't find the Higgs boson experimentally, then the whole theory is useless, doesn't work. So the Higgs boson was predicted already back in 1964, and so let's say essentially after in the 70s and essentially after the 80s, it became, let's say, the main priority of all high energy physics experiments. So the search for the Higgs boson. The discovery, as you all know, was announced in 2012, in July 2012, at CERN, by simultaneously the ATLAS and the CMS experiment at the Large Hadron Collider. They found sufficient evidence, actually proof, it was beyond the 5 sigma discovery level, of a new scalar particle, okay, in the within the expected mass range, the most probable mass range at the time. And this was discovered essentially at the time in two main channels that we study. One of those is shown here. So it's the Higgs decaying into two photons. And so when you reconstruct, when people reconstructed the invariant mass of these two photon system, they found a little bump here corresponding to an invariant mass of 125 GeV. Okay? And a similar bump, this is just an example from CMS, similar results have been obtained by Atlas. And another channel that was also exploited for the discovery of the Higgs boson was the Higgs decaying into two Z bosons, further decay into pairs of charged leptons, 4 charged leptons. So these are not the most probable decay modes, as we will study. These are actually quite suppressed, especially this one in two photons, but they have the advantage of being very clean. So this allows to subtract quite easily the huge background. And so although the probability is quite small, it's very small actually, you still are able to suppress the background and to find this little signal here, okay? And the two masses, so TMS and others found the varied mass 125.3, 126, which are of course absolutely consistent within each other within the experimental uncertainty. Today, the precision, after 8 years of data, of new data, the precision is of course increased, and the decay of the Higgs boson has been observed in many other decay modes. Okay. Now, as a result, the following year, so in 2013, Higgs and Henger got Nobel Prize, and the motivation was for the theoretical discovery of a mechanism that contributes to our understanding of the origin of subatomic particles. Actually, Brute, who also contributed to the development of the Higgs mechanism, unfortunately died the year before, so he could not get the Nobel Prize. The Nobel Prize can only be awarded to living people, as you know. So this picture summarizes all I've told you so far. So there are two different types of matter, okay, types of particles, sorry. The matter particles and the force particles. The matter particles we divide into leptons and quarks, and the force are the gauge bosons of the three interactions, so the photon, the Ws and Z, and the gluons. And the blue line that you see here in this picture tells you how things interact with each other, okay? So for instance, the quark, which carry electric charge, weak charge, and strong charge, they interact with to the gluons, to the Ws, the Z, and also to the photon. The leptons only have electric charge and a weak charge, so they interact only weakly and electromagnetic to the photon and the Z. And all the massive particles, so leptons, quarks, and heavy boson interact with the Higgs field, okay? Whereas there is no connection, as you see, from the photon to the Higgs and from the gluon to the Higgs, because the photon and the gluon are massless. And then you also find some self-interactions like these. Also the Higgs is a massive particle, as we have seen, 125 GeV, so it must interact with itself. We will study this self-interaction. Also, there is a self-interaction from the gluon, because the gluon carry charge, differently from the photon, which do not carry electromagnetic charge. And so the gluon, as we will study, also self-interact. All right. So, as I was anticipating, this was just an appetizer. So it will take the whole semester to study in detail everything I showed here in the last 20 minutes, okay? Do you have questions so far?
Yes, if I may ask.
Sure.
Why is there a self-interaction between the W's and not with the Z?
Because W's carry the weak charge also, this weak isospin. This will be studied at the end of the course, so they can also self-interact. What is not observed is an interaction, for instance, and they also interact with the photon, as you can see, because they are electrically charged, W plus, W minus, whereas there is no interaction observed between the Z and the photon. Okay.
Thank you.
You're welcome. So if you don't have further questions on this part, let me go on and let me discuss now briefly accelerators and the Large Hadron Collider, which is the place where now the majority of the high energy physics experiment results are arriving from. So particle accelerators have a dual scope, essentially. One of those is that they act as extremely powerful microscopes. So you can use an accelerator to inspect in very detail the structure of a hadrons, for instance. And why this happens? Well, this is because, as you know, subatomic particles are known to have a dual nature. This you know already from quantum mechanics. So they can behave as a particle and also as wave, and this was already discovered by de Broglie in 1924. So it is possible to associate to each particle a wavelength that we call the de Broglie wavelength, which is the ratio between the Planck constant and the momentum, as you all know. So now the spatial resolution is provided by the de Broglie wavelength of the particle beams, okay, and it is inversionally proportional to the particle momentum. This implies that the higher the momentum of your particle beam, the higher the capability to observe smaller and smaller details. But there is also another reason to construct and to use accelerators, that is to, of course, discover new particles, okay, and generate new particles in the collision. And this is, of course, possible thanks to the well-known mass-energy equivalence, okay, from special relativity. Essentially, suppose that you have two colliding beams, okay, from one side or from the other, or a beam colliding on a fixed target, doesn't matter, okay. If the particle beam energy is sufficiently energetic, and so if the center of mass energy is sufficiently high, then the energy released in the collision can be converted into the mass of new particles. And this is the reason why essentially the Large Hadron Collider was built, okay, because there was a quest for the search of the Higgs boson, at least, and also for supersymmetric particles, whose mass was expected to be higher than that could be reached from other laboratories like Fermilab, etc. And so we need to push ahead the energy frontier in order to be able to produce such massive particles. Okay, of course, we also take into account not only the mass of the particle, but also the probability, so the cross-section to create it, which is extremely small. So what is Large Hadron Collider? It is, as you know, the highest energy particle collider ever built, and it is also the highest luminosity proton-proton collider to date. It has been realized in 2 decades by more than 10,000 physicists and engineers from 85 different countries. And in the machine, protons are accelerated at nearly the speed of light, like 0.9999998 of the speed of light in the vacuum, and experience more than 11,000 revolutions per second in a 27 kilometers underground ring. I guess this you know, everybody. And protons from the 2 beams, so we have 2 beams rotating in opposite direction, okay? So they collide something like 40 million times per second. A few words about the operation. So LHC started its operation in 2010, okay? And so there was a first run called the LHC Run 1 from 2010 to 2012 with the center of mass energy ranging from 7 TeV up to 8 TeV. Then there was a very long first shutdown, okay? That took essentially more than 2 years. And LHC restored the operation in 2015 up to 2018 with the so-called Run 2, where now the energy of the center of mass in the collision was raised up to 13 TeV, which is almost the nominal construction limit. And this limit, which is 14 TeV, we hope to reach in the next run. So at the moment, as you see, the machine is off. It is in an upgrade phase. This is called the long shutdown 2, and operations will start again, hopefully in February 2027. Okay, so there will be another long run up to 24, where we expect that the energy could be even higher, so up to 14 TeV in the center of mass. LHC is only the last part of a complex chain of accelerators. So everything starts, I think, in this point here, okay? So there is a bottle of hydrogen gas. The hydrogen gas is then stripped from the electron, so you get protons. protons are positively charged, so they can be accelerated in an electric field. And this is what essentially is done in this LINAC. Okay, it is a linear accelerator that provides the first acceleration step of the protons. Then the protons are injected into the proton synchrotron, okay, where they rise further their energies. When they get the proper energies and also the proper intensity, the beam is injected into the super proton synchrotron, okay, which is the machine essentially with some modification where the W and the Z boson have been discovered in the early 80s. And here, when the energy of 450 GeV is reached, they are eventually injected into the Large Hadron Collider, okay? And here the energy increases even further, reaching something like 6.507 TeV per beam. Now, CERN, as you know, is located in the border between Switzerland and France. Is in the western periphery of Geneva. You see here, I think everybody has seen this picture already. So you see the Alps in the background, the Geneva Lake here, the Geneva Airport here. And this yellow ring indicates the position of the Large Hadron Collider, which is, of course, not in the surface, but it is 100 meters underground. This funny picture shows you how the LHC compares with the size of Ferrara. So this is the ancient wall of Ferrara, and you see how huge is this accelerator. So there is a circumference of 27 kilometers. This is a view of a section of the machine. Okay, and what you see here, these blue objects here are the cryostats of the superconducting dipole magnets that are needed, of course, to maintain the protons in the circular orbit. And these are, of course, let's say, jewels of technology. First of all, they have to provide a very intense electromagnetic field of the order of 8 Tesla in order to maintain 7 TeV protons in a circular trajectory. There are more than 1,200 of these magnets along the ring, and they work at the superconducting regime at the temperature of the superfluid helium, which is 1.9 Kelvin. And so LHC, turns out that it contains the world's largest cryogenic system, okay? And it also constitutes the coolest place in the universe. You know that the temperature of the universe is roughly 3 Kelvin, and here there is a huge tank of helium at less than 2 Kelvin. The picture you see here is the two beam pipes, so where the two proton beams circulate in opposite direction, surrounded by these supermagnetic coils. This is an overview of the machine and also the experiments. So the ring is under 100 meters underground, okay, and it crosses the border between Switzerland and France, and it serves 4 main experiments: the CMS Atlas that I already mentioned for the discovery of the Higgs boson, and also LHCb and ALICE. A few words about how one such particle detector works. This I expect you know already, let me just remind you. So when you have a collider, the typical geometry of the detector is like this. So you have different layers of different kind of detectors. So the beam interact at the center of the detector, so they come from opposite direction and they interact here in the center, for instance. So the first layer, the one you see here in green, is dedicated for the tracking. So there are detectors, mainly silicon detectors or temperature projection chambers, which are needed to reconstruct the tracks of the charged particle within a magnetic field. The magnetic field is provided typically by a solenoidal magnet like the one shown here. So by measuring also the curvature of the tracks, you are able to measure the momentum of the charged particles. Then the red layer is the electromagnetic calorimeter, which is needed to measure the energy of electrons and essentially photons. Okay. Then we have where they, of course, they generate electromagnetic showers inside the volume, the sensitive volume of the detector. Then this light green object is the so-called hadronic calorimeter, which is used to measure the energy of hadrons. And finally, then we have the magnet, then we have the iron joke of the magnet, and between the iron joke of the magnet, we have the muon chambers, typically. And the reason why the muon chambers are so outside is because they are, apart from the neutrinos, which completely escape the experiment, the muons are the most penetrating particles producing the interaction. So they completely cross the full detector volume, and they are the only particle that can leave some signal in these outer layers. Okay, this we can see also here even better. So for instance, let me start from, suppose you produce an electron in the collision, so the electron will leave some signal in the tracking system because they are charged particles, and then they release their full energy in the electromagnetic calorimeter. If you create photons, photons are chargeless, they're neutral, so they don't leave any signal in the tracking system, and they release all their energy in the electromagnetic calorimeter. If you create charged hadrons, like protons, kaons, pions, etc., then they provide signal both in the tracking system. Part of the energy is released in the electromagnetic calorimeter, and the rest of the energy is released in the hadronic calorimeter, where they are fully stopped, completely absorbed. Then you might also have neutral hadrons, like the neutrons or the K0. So again, they are neutral, so they do not leave any signal in the tracking system. They release some energy in the electromagnetic and most of the energy in the hadronic system. And then finally, you have the muons. The muons are the most penetrating one. They cross the full detector, so they leave some signal everywhere in the detector, and they escape. They are not stopped in the material. Few words about the main experiment. So this is an overview of the Atlas detector. It is the largest and most complex particle detector. It is really huge. So consider the dimension of the size of people here, persons. So it's like a cathedral. It's 46 meters times 25 with 7,000 tons weight. And the structure of the detector is essentially the same I was showing before. So it is, we have layers. Inside we have the tracking system, then we have the calorimeters, and then we have the muon at the very end. This is a very impressive picture of the toroidal magnet of the Atlas experiment. This is a photo was taken during the construction period. And now the second is CMS. CMS is also a huge, gigantic detector, although it is quite smaller than Atlas, so it's half the length essentially. But it is much heavier. It is 14,000 tons because it contains a lot of iron in the return joke of the magnet. And it is specialized for detection of muons, but of course it can detect everything. It is a general purpose detector. The structure of the CMS detector you can already see here, but it is even more clear in this second slide here. So again, we have the tracking system, which is made by a cylinder of silicon pixel detectors or strip detectors, okay, in the very inner part, so the collision occurs here. Then we have, for instance, electrons that leave the signal in the tracking and the electromagnetic calorimeter. Then we have the hadrons that leave the signal in the tracking and the hadronic calorimeter. We have neutral hadrons that only leave signal here, or photons that only leave signal in the electromagnetic calorimeter. And again, we have also muons that cross the detector and leave signal everywhere, including also the muon chambers, which are outside the magnet. This is the magnet. Here's another impressive view of CMS during construction. And this table summarizes the main features about Atlas and CMS, so the total weight, the overall size, etc. There is also an estimate of the cost, so I think it's completely obsolete, 550 million Swiss francs. Now, there are two other experiments at the Large Hadron Collider. One is ALICE. So the other two are more specialized experiments. So CMS and Atlas can do everything. They are general purpose detector, so they are good for everything. And then there are two specialized experiments, which are ALICE and LXCB, which are mainly, but not only, optimized for specific searches in particle physics. So this is an overview of ALICE, which is still a very large detector, and it is made by two parts. The central part is, again, the standard cylindrical collider detector with different layers. Here, the main tracking is provided by the time projection chamber, which is the largest in the world here. And then there is also a forward spectrometer, which is mainly dedicated for the detection of muons. And okay, so this is a picture of ALICE. And so ALICE is mainly taught for studying ultra-relativistic collision of heavy ions. So LXC not only accelerates protons, but can also accelerate ions as heavy as lead. So we can have proton-proton collision, proton-lead collision, and lead-lead collision. And ALICE was specialized for studying these huge lead-lead collisions, where you see the multiplicity of the tracks that you produce in every collision is incredible. You have thousands of tracks per collision. Okay, and the reason for this, as what we study, is to search for signals of the so-called quark-gluon plasma. That is a status of the matter where hadrons are not formed, and quarks and gluons are essentially free to move inside this plasma, which is expected to have been created in the very earliest ages of the universe. Well, earliest means smaller than 1 microsecond after the Big Bang. And then the last one is LHCb. LHCb, as you can see from this picture, has a completely different geometry. It is not anymore cylindrical. It is not symmetric. It is so-called a forward spectrometer. So it is, as you see, it is a forward geometry. So the beams come again in the central line, and they interact in this point here. Okay. So this interaction point is surrounded by a very sophisticated tracking system, which is called the vertex locator, which allows to reconstruct with high precision the vertex from the collisions. Then we have a big dipole magnet here, and we have a tracking system before and after the magnet to reconstruct the momentum of the particles. Then we have all other detectors which are needed for the particle identification. So also here we have electromagnetic and hadronic calorimeters. We have the muon chambers in the very most external layer. And we do also have here 2 detectors in yellow, which are the rich detector, which exploit the Cherenkov effect to disentangle and to discriminate between pions, kaons, and protons. Now you see a picture of the detector inside the cavern, and this is only a small part of the collaboration, which is more than 1,000 people. And let me conclude with a few things about the units. So as you know, the electron volt is the energy acquired by an electron in a potential difference of 1 volt, okay? And it corresponds to a very, very small energy, 1.6 10 to the minus 19 joule, as you know. So in physics, we work mainly with multiples of the electron volt. So the keV, it is 1,000 of electron volt, and this is the range of atomic physics. The MeV, or mega electron volt, 1 million electron volt, this is the range typical of nuclear physics. The GeV, or GeV, 10 to the 9 electron volt, so a billion of electron volt, and this is typical of experiments that study hadron structure. And then we have the TeV, 10 to the 12 electron volt, which is the typical range for particle physics experiments. Let me remind again that at LHC, the 2 proton beams with an energy of 6.5 or even 7 TeV collide, resulting in a center of mass energy of 13 or up to 14 TeV, which is the highest energy obtained at an accelerator on Earth. If you want to study nowadays more energetic phenomena, you cannot do them in accelerators. You have to look on the cosmic rays. Length are measured in Fermi, and 1 Fermi is 10 to the minus 15 meter, which is roughly the size of the proton. It is also useful to remember this conversion that we will use a lot in solving exercise. So h bar c is order of 200 MeV per Fermi, or 0.2 GeV per Fermi. So this is also easy to remember, and this we will apply several times. About cross-sections, you know that cross-section is measured in barn, and 1 barn is 10 to the minus 24 square centimeters, which is 1 barn is an incredibly high cross-section. So we will, of course, work with submultiples. So the picobarn, which is 10 to the minus 12 barn, and the femtobarn, which is 10 to the minus 15 barn, are typically used in elementary particle physics. Okay. And then finally, we will adopt, in many cases, the natural units. So we will, for simplicity, use h bar equal 1 and c equal 1, where c is the speed of light in the vacuum. Okay, let me stop here for a few minutes. You are free to ask questions if you have. No questions? Okay. Obviously, most of these things you already know from previous studies. So we can take maybe 2-3 minutes break, and then we continue with we will now start attacking the relativistic kinematics. Again, this will be a reminder of things that you already know from previous studies, so nothing new today. Okay, so let's stop for 2-3 minutes. Okay, I think we can resume the lesson. Can you still hear me?
Yes.
Thank you. All right. So, as I was saying before, let me start now with the first module of the course. That is just a simple reminder of actually special relativity today and relativistic kinematics tomorrow. I think what I will show today you know already perfectly. Maybe what I will show tomorrow will be new for some of you. So, why relativity? Particle physics deals in general with very energetic processes, as you know, in which particles are produced and propagate with velocity which are close to that of light. And this is the reason why they must be treated as relativistic objects. So let me just draw down the principle of the special relativity provided by Einstein in 1905. So the first one is the law of physics are the same in all inertial reference frames. That means in all reference frames moving with a constant velocity with respect to each other. This is clear and well known. The second is also clear and well known, is that energy, linear momentum, and angular momentum are conserved in all isolated systems. And this you know also very well. And these two first principles are common to classical physics, so to non-relativistic physics. Now the new things arrive. The velocity of light in vacuum is a constant in all reference frames, and it is equal to the value you see here, although we will use for exercise the approximation of C equal to 3 × 10⁸ meters per second on 10 to the 23 Fermi per second. So whatever reference frame you use or you observe from, you will always get this value of the speed of light in a vacuum. And this is, of course, a revolution. And the other revolution is that time is not a relativistic invariant. This means that the flow of time depends on your reference frame. So the principles 1 and 2 are common to classical physics. However, in classical physics, time is a relativistic invariant, so it flows uniformly in all reference frames. But of course, the speed of light cannot be universal if there exists a universal time for all observers. So fixing the speed of light for all observers means that the time cannot flow uniformly to all of them. Special relativity is based on the space-time transformation properties of physical observables as measured in inertial frames moving relative to each other. So let me start drawing two of these frames. So let's consider two reference frames, the O x y z and O prime x prime y prime z prime. And we suppose, for simplicity, they coincide at time t equal t prime equals 0. Okay, so they are just overlaid at time 0. And they move with respect to each other with a constant velocity v along their common x direction. So this is the most simple thing you can think of. And so the two observers, one on one frame and the other from the other, want to study, for instance, an event. Now, let me define the 4 vector as an object which is defined by 4 components that transforms from one reference to the other under the Lorentz transformations. So a 4 vector is an object that is completely described once you define these 4 coordinates. The first one is the time-like component, and the other 3 are the space-like components. We can write it in the compact way as a mu, where mu is the Lorentz index that spans from 0 to 3, where 0 is always the time component. And we can also write in this compact form, like the time component alone and the 3 we collect as a vector. Okay. So again, a 4 vector is an object defined by 4 components that transform from one reference to the other under the Lorentz transformation. And these are the Lorentz transformation that you know very well. So suppose you want to know the components of the 4 vector in the prime frame, and you know those in the unprime frame, then you need to apply this transformation law, where gamma and beta are, beta is the ratio between the velocity and the speed of light, and gamma is defined as the Lorentz boost, defined as 1 divided by square root of 1 minus squared beta. So when you now do this cross product, we obtain now this vector of transformed coordinates. Okay, and the striking thing of the Lorentz transformation is that they mix the first two components of the four vectors. Okay, so they mix A0 and A1, and A2 and 3 remain unchanged, as you see, because we are in the simple hypothesis that the two frames are moving only along the common x direction. One major example of four vector is the position four vector that we can indicate as x mu, where the time component is ct, so speed of light and time, and then we have the three spatial components. And by applying the standard Lorentz transformation, we obtain the transformed component, okay, ct prime, x prime, which again mix the first two components of the four vector, and the other two remain unchanged. Now, it is interesting to note that for non-relativistic particles, when beta is much, much smaller than 1, and so gamma is almost 1, so when you apply this to the Lorentz transformation, you obtain back the classical Galilean transformation, okay? So the first one, you put beta very small than 1, so that you can elect this term, you can simplify C, and you essentially get gamma is 1, you get just that the time is uniform, okay? Does not depend on your reference frame. And then you get the standard Galilean transformation when, again, you go in this limit. So the Lorentz transformation are, of course, more general. They work perfectly for a highly relativistic object, but they also include the classical Galilean transformation as a non-relativistic limit. Let's consider now the more general case where the two reference frames move along an arbitrary direction, although keeping the axis parallel, okay? So as you see in the picture, so you want to study, for instance, an event in the point P, and the vector position are R prime in the prime vector and R in the unprime vector. And this is the position vector of the second frame with respect to the first one. Now, only time and the coordinates which are parallel to the direction of the relative motion will change in the Lorentz transformation, as we've seen already in the simple example before, whereas coordinates which are perpendicular to the direction of motion do not change. So this was already clear here because the y and the z remain unchanged in the transformation. Okay. It is less obvious here, but then of course one can always redefine the position vector in terms of a component which is parallel to the direction of motion and another component which is orthogonal or normal to the direction of motion. Okay, this you can always do. And so when now you apply the Lorentz transformation, it turns out that the transformation only involves the component which is parallel to the direction of motion and leaves unchanged those that are transverse, orthogonal. Okay, so as an example, the transverse momentum of a particle is a Lorentz invariant. Now, as you know already from your previous studies, there are two important consequences of the Lorentz transformation. The length contraction is the first one. So an object of length L prime, which is in motion with respect to an observer, appears to be contracted to the observer by a factor 1 over gamma. So the length, the observed length, okay, is L prime divided by gamma, where gamma is obviously greater than 1. So you get a contraction of your length. And the counterpart of this is the time dilation. So if delta t prime indicates the time interval between two events occurring in the prime system, the corresponding time interval measured by an observer in the fixed system is longer. We have a time dilation, and it is longer again by a factor of gamma, which is greater than 1. Now, the time measured in the prime system is said the proper time, and it is usually denoted by the Greek letter tau. So again, when we apply the time dilation, the t measured by the fixed observable is gamma tau. In relativity, the simultaneity of two events depend on the reference frames. So in the sense that two events may be simultaneous in a reference frame, but not in another one. And this we see even better later on with the light cone. Now, a notable example of time dilation and length contraction is given by the decay of atmospheric muons, which are producing collision of cosmic rays with the atoms in the atmosphere. So you know that cosmic rays are extremely high energetic particles, such as protons, but also light nuclei, even up to iron. that are produced in extremely energetic phenomena in the cosmos, okay, like a supernova explosion or whatever. They travel around the universe. Of course, they are deflected by magnetic fields around their path. And some of them, of course, reach our Earth. And when they arrive here, they interact with the atoms of our atmosphere, which are mainly hydrogen and helium. And they give rise to very high energetic interaction processes, which result in secondary particles, which further decays. And so at the end, we observe a shower of particles that, as you know, arrives up to the Earth's surface. So again, I was also saying a notable example of the time dilation and length contraction is given by the decay of atmospheric muons, as seen by the muon reference frame or by a reference of unobserved, which is at rest on Earth. So let me now solve an exercise on this. So we now move on to the blackboard. So let me first go through the text. So a muon is created in the atmosphere at an height of 10 kilometers from the Earth's surface and propagates through the atmosphere with 98% of the speed of light in vacuum. Considering its proper decay time of 2.2 microseconds and indicating with T of T prime, the time needed to reach the Earth's surface as measured by an observer at rest on Earth or by the muon rest frame, then we are asked to calculate the ratio T prime over tau in the muon reference frame, the ratio capital T over T in the reference frame of an observer which is at rest on Earth, and then the last request is the number of muons which had decayed before reaching the Earth's surface, if one assumes that 1 million muons are produced simultaneously at 10 kilometers from the Earth's surface. So now let me try to switch. No, interrompi condivisione. Ok, da casa riuscite a vedere adesso la lavagna? Cosa vedete?
Sì, la vediamo.
Quindi-
Dovrebbe fare delle prove, poi le diciamo magari se non riusciamo a vedere il tratto, ad esempio.
Sì, perché ho visto prima che il tratto è molto debole purtroppo, quindi sarà un po' un problema. Per la prossima volta proveremo ad attrezzarci con delle lavagne grafiche.
Sì.
Allora,
Il blu ieri era più forte.
come dici, scusa?
Il blu ieri si vedeva meglio, il pennarello blu.
Ok, partiamo col blu allora. Okay. All muons are created in the atmosphere at 10 kilometers from the Earth's surface, okay? And of course, muons are unstable particles, they decay, okay? Do you know by chance the decay mode of the main decay mode of the muon? As we will study, of course, later in the course, the muon decay is regulated by the charge current weak interaction. So if you have a muon, this indicates into an electron plus an electron antineutrino plus un muon neutrino. Riuscite a vedere a casa?
Sì, vediamo.
Ah, ok, non me l'aspettavo. Okay, so let's first let's first calculate now the gamma factor, the Lorentz factor. So we know that the muon is traveling through the atmosphere with a speed of 98% of the speed of light. So d is equal to 0.98. Okay. This means that beta, which is d over c, is 0.98. And when you calculate the gamma factor, this is 1 divided square root of 1 minus beta squared. This turns out to be order of 5. All right. So now let's first try to answer the first question. Okay. Let me read again the text. So the ratio of the time divided by the time of the muon of the decay time of the muon in the muon reference frame. So we work now in the muon reference frame. So the muon is traveling fast through the Earth atmosphere, okay, pointing to the Earth's surface. So from the muon reference frame, the atmosphere is moving against him. There. And so the muon sees the atmosphere Lorentz contracted. So the length of the atmosphere seen by the muon reference frame, that we call L prime, okay, is the contracted length. So this is the real length, L0, divided by the gamma factor. So L0 we know is 10 kilometers, so this is 10 to the 4 meters, and gamma is 5. So the thickness of the atmosphere seen by the muon is just of 2,000 meters. All right? Now let's calculate the time that needs the muon to reach the Earth's surface. So we know that the velocity is space over time. So we derive the t prime as L prime over b. So let's just substitute this. So we have 2,000 meters, which is the thickness of the atmosphere as seen by the muon. And the velocity we know is 0.98 times the speed of light, that is 3 × 10⁸ meters per second. And when you do the calculation, you obtain 6.8 10⁻⁶ seconds. That is 6.8 microseconds. And so now we can calculate the ratio between this time and the proper decay time of the muon divided by tau. This is given by the text, so this tau is 2.2 10⁻⁶ seconds, or 2.2 microseconds. So we can calculate this ratio, and we get 6.8 microseconds divided by 2.2 microseconds, which turns out to be approximately 3.1. Or in other words, the time needed to the muon to reach the Earth's surface is 3.1 times its proper decay time. And this means that most of the muons will have decayed in flight before reaching the Earth's surface. Okay, the majority. Ditemi quando, da casa quando posso cancellare. C'è ancora qualcuno che sta copiando da casa?
I don't know, but I think it's okay.
Okay, I can clear the board.
Yeah.
Va bene per me.
So do you all see clearly what is written on the board?
Yes.
Yes.
Okay, so maybe we don't need the tablet. So if this works, is fine for everybody, then it's even the easiest solution. I will try to use to write it large if I can. So okay, very good. Okay, so this is the result. Let me write it here from the muon reference frame. T prime is equal to 3.1 tau.
Professore, scusi,
Sì?
l'unica cosa è che quando poi appena girato verso la lavagna si fa più fatica a capire quello che dice.
Ah, cioè non mi sentite bene quando mi lontano?
Si sente ma non quindi...
Vediamo un po', perché il cavo è corto qui. Posso provare a mettere un po' più vicino qui e parlare un po' più forte, perché di questo non riesco a fare. Cioè, avvicino un po' il cavo, ma ecco qua, così. Questo mi sa che è il massimo che riesco a fare. Okay, let's now describe the same problem now from the point of view of an observer which is at rest on the Earth surface, and so also at rest with respect to the atmosphere. So now an observer sees the atmosphere at rest and sees an incoming muon. So as we've seen, the time is in this case dilated by a factor of gamma. So the observer at rest sees the muon decay time multiplied by gamma. So this is the muon decay time as seen by an observer at rest on Earth. And so we have 5 times 2.2 microns, which is 11 microseconds, sorry. Right? Let's calculate again the time needed to the muon to reach the Earth's surface as seen by an observer at rest on Earth, so T. So this is L0 divided by V, because now the observer of Earth sees the full length of the atmosphere, which is 10 kilometers. Okay. So this is 10 to the 4th meter, divided again 0.98 times 3, 10 to the 8 meters per second. And the result is 3.4, 10 to the minus 5 seconds, or essentially 34 microseconds. So according to an observer which is at rest on Earth, it takes 34 microseconds for the muon to reach the surface. Let's now again calculate the ratio E over T, so the time to reach the surface divided by the decay time as seen by the observer at Earth. And so we have here 34 microseconds divided by 11 microseconds. Oops. That is again 3.1. So again, T is 3.1 the decay time, also in the case of an observer at rest on Earth. So essentially, the muon sees the atmosphere contracted, the observer on Earth sees the decay time dilated, but they both agree that it takes 3.1 times the decay time to reach the surface. Okay? Now we can go to the last request, the point C. Aspetto qualche minuto così finite di copiare. The request C is the following. Let me just read again. So the number of muons decayed before reaching the Earth's surface, assuming that 1 million muons are produced simultaneously at an height of 10 kilometers from the Earth's surface. Posso cancellare? Ok, se non sento obiezioni vuol dire che posso cancellare. Here you have to remember, of course, the decay law of unstable particles, which is the usual exponential decay law, okay, from the case. So let's now answer the question C. So from the muon reference frame, the number of survived muons after a time t prime, so once reached the Earth surface, is given by the total number of produced muons times e to the minus t prime over tau. This is the standard exponential decay law. Okay, so we can calculate this easily. So we have 10 to the 6, as we know from the text, and then e to the minus 3.1. And this turns out to be 4.5, 10 to the 4. So this is the fraction of muons that survived, that arrived on the Earth before decaying, essentially. Okay. Let's now sit on the observer on the Earth again, and surdo at t is equal to n0 e to the minus t divided by small t. And it is exactly the same as we have just shown. So this is 10 to the 6, e to the minus 3.1, and again 4.5, 10 to the 4. So they both agree that only 35,000 muons will reach the Earth's surface. Now, the question was actually to calculate the number of muons that have decayed, so the complement of this. So the number of muons decayed is just the number of muons that have been produced, so n0, minus those that survived. Okay, so in both cases, we're going to have 10 to the 6 minus 4.5, 10 to the 4. And this results 955,000. Okay, so the large majority of muons indeed has decayed in the path from atmosphere to Earth. And the reason for that is that the time it takes for the muon to reach Earth is more than three times the decay time of the muon. Okay? Ok. Autorizzate a cancellare? Sì. So let's continue for the moment on the blackboard. Okay, the theory. So we are now back on the theory. So we introduced already the 4 vectors. Okay, but there are actually 2 kinds of 4 vectors, as you know. So those that are denoted in this way with the index above, which are the type x0, x1, x2, x3. And these are called the contravariants. Or vectors. But there is another type, okay, which is the one denoted with the index on the bottom, where now the spatial components come with an opposite sign. So it's x0 minus x1 minus x2 minus x3. And these are called the covariants for vectors. And of course, the two are linked each other through this simple relation. So x mu is equal to g mu nu x nu. So we have here the contravariant is equal to the covariant through some object that is the metric tensor of the relativity. So g mu nu is defined this way. It's 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, and 0, 0, 0, minus 1. Okay, so we have a 1 in the first element of the diagonal and a minus 1, which provides the sign change when you want to link the contravariant and the variance for vectors. Now, this is relevant because you need actually both. You want to define the scalar product of two 4 vectors. So let's define the scalar product and see what are the main properties. So suppose we have two 4 vectors, capital A and capital B. Okay, we define the scalar product as an operation between 4 vectors defined in the following way: A, I move, B move, or equivalently, A move, B move. Okay, where the one is the contravariant, the other is the covariant, or vice versa. And of course, here we are implying there is a sum over the Lorentz index move, which is implied here and here. Okay, we don't put it for simplicity. So we have to sum for move equals 0, 1, 2, and 3. Okay. Now, it turns out that the scalar product is a relativistic invariant. This means that it remains unchanged when changing from one reference frame to another reference frame through the Lorentz transformation. Okay. And this let me just start the proof, and then I will continue the proof yourself. So suppose now we work in the prime, so A prime times B prime. So you want to calculate the scalar product in the prime reference frame, knowing the components of A and B in the R in prime reference frame. Okay. So this is by definition. So we are now using this definition here. A0 prime, B0 prime minus A1 prime, B1 prime minus A2 prime, B2 prime minus A3 prime, B3 prime. Okay. Now we apply the Lorentz transformation because we want to relate these to the component of the same object but in the reference frame. Okay. So we're going to have here gamma A0 minus beta A1. So again, we are mixing now the first two components times again gamma B0 minus beta B1. And this is the first list. Now again we have gamma minus gamma A1 minus beta A0 times gamma B1 minus beta A0. Again, we are mixing the first two components. And then we have the unchanged task that is A2 B2 minus A3 B3. Okay, I will not do now the calculation. It is now simple algebra, but you do as an exercise. Okay, so you do, and just show that all this is simply equal to A0 B0 minus A1 B1 minus A2 B2 minus A3 B3. That is the scalar product in the other reference frame. Okay. The two are equal. This means again that the scalar product is a Lorentz invariant, so it remains unchanged in two Lorentz transformations. Few more things. Suppose now that the two 4 vectors are equal. So BE is equal to 1 to A. So we calculate the scalar product of a vector with itself. So what we obtain is A star A equal to A move move. It is A0, A0, minus A1, A1, minus A2, A2, minus A3, A3. We're just applying the definition of the scalar product. So this we can also write, since these are the same, as A0 squared minus A1 squared minus A2 squared minus A3 squared. And this we can write in a compact way as A0 squared minus, we have the modulus of the vector A squared, which includes only the spatial components. It is nothing else than A squared. So the result is that the square of any 4-vector, okay, is nothing else than the scalar product of the 4-vector with itself. We have shown, actually you will show that the scalar product is a Lorentz invariant, and so also the square of any vector, 4-vector, is a Lorentz invariant. Remain unchanged when applying Lorentz transformation from one reference to the other. And there are 3 possibilities. The first possibility is that A squared is positive. Okay. And so the vector I is a time-like vector. Time-like vector. The other possibility is that A squared is negative. And so A is a space-like vector. And the last possibility is that it is null. Okay, and so A is a null vector. And let me now describe this in some more detail through the slide. So let me go back to the slide. Dove sta? Riuscite a vedere la slide da casa?
No.
Perché non ho fatto così, ok, una finestra, giusto. Adesso? Riuscite a vederla? Perfetto. Allora, questo è il testo del problema che abbiamo risolto prima. Quando nelle slide trovate il simbolo della lavagna, vuol dire che c'è una parte che non è mostrata sulle slide, ma che sto svolgendo la lavagna, ok? Quindi nei vostri appunti andare a cercare poi di... Quindi questo vuol dire che le slide non contengono tutto il corso, ma solo una parte, ovviamente. So, to clarify the concept of time-like and space-like, let's consider 2 4 vectors describing the position of 2 events, event O and event P, in space-time, okay? So event O we characterize by this 4-vector, and event P by this other 4-vector, okay? Where again we denote the time-like component and the space-like component. So once we have 2 events, we can define the Lorentz invariant relativistic interval, okay, between these 2 events, that you can construct in this way, okay? And it is easy to show that this is again a relativistic invariant that does not change from one reference to the other. And now we have these 3 possibilities. So the space-time displacement vector that joins the O and P events is said to be time-like if the relativistic interval is positive. And this can only be possible if the events are separated more in time than in space. So this object here can be only possible if this first term is greater than the sum of the others, obviously, okay? So the timeline component is dominant in this case. In the opposite case, our displaced vector is called space-like if now this relativistic interval is negative, and this can only be possible if the spatial component, okay, the space-like component is greater than the time component, again. And then it is light-like if the interval is equal to 0, okay? In this case, the space-like and the time-like component of the displaced vector have the same importance, clearly. So the difference goes to 0. And this we can visualize. Okay, let me. Okay, so being a relativistic invariant, being the relativistic interval a Lorentz invariant, if an event P is time-like or space-like in a given reference, it will be time-like or space-like in any reference frame. So let's visualize this even better in the light cone. Okay, so this is the time direction. This is the two spatial directions, and this is the light cone. Okay, so this is essentially the surface covered by light signals emitted from O. So they will describe a cone here. Okay, which is 45 degrees with respect to the plane, to the XY plane. So here we can see, first of all, two cones, the future cone and the past light cone. Suppose now we have an event. So the first event is O, it is at the origin. Suppose now we have an event P, which is inside the future light cone. Okay. So a time-like vector connects two events that are causally connected. This means that the event P is influenced by what happened at the event O. They are causally connected. Okay. So the second event is inside the light cone of the first event. Given two events that are time-like separated, it is possible to find a frame in which the two events happen at the same place, but not at the same time. And this will be not possible in any reference frame, because delta S is a Lorentz invariant. The other possibility is that now your second event P, is outside of the light cone. Okay. So in this case, the displacement OP is a space-like vector. It connects the two events that are now causally disconnected, in the sense that the second event, which is outside the light cone, is not influenced by the first event O. Okay, and it will be never influenced in any reference frame. The temporal order of space-like separated events depends on the frame in which the events are viewed. It is always possible to find a frame where they appear simultaneously, but it is impossible to find a frame in which they happen to be in the same place. Okay, so this is the main difference between time-like vectors and space-like, and we will find some of them during our course. That's why I want to specify this now. Okay, this I think is the last slide. Yes. Do you have questions? If not, we can stop here, and we resume tomorrow at 11, right? So, so if you all guys at home confirm me that you could clearly see the blackboard, then we can continue in this way. Do any of you had problem in seeing the blackboard? Hello?
That was okay for me.
Thank you. Okay. So this will be the easiest solution also for my side. Okay. And blue is the winner, apparently. Okay, then if there are no questions, I will now stop the registration of the lesson, and we will see you tomorrow.
Thank you very much.
Thank you. Have a nice day.
Thank you. Have a nice day.
Bye.
Bye-bye.